Hi, old David here. I decided that since I won't be, since as I mentioned in last week's session, I will be on a plane somewhere between Perth and Sydney on Wednesday night at the time of our Collaborate session. I'm going to Curtin University in Perth to help with the review of their School of Education. Most faculties and schools in universities are required to do an annual review a 5-year rolling review process just to see how they're travelling, to get some external expertise to check what they're doing. So I'll be doing that for the first 3 days of next week, and then the Australian Council of Deans of Education is meeting in Sydney for the last 2 days of next week. So I'll be in Perth and then in Sydney, and as I say, in the air at the time when I would normally be leading this Collaborate session. So I'm going to record it and pop it up on YouTube instead, so you've got the opportunity to watch it and obviously at any time that you prefer, rather than between 5 and 6 on Wednesday. So hopefully that'll be convenient as well. This is the second last of our sessions, so it's been a long and interesting one, hopefully a useful one. I can see more and more people are finishing up the quizzes. I marked a couple today. I'll actually go in and set it up so that it doesn't worry about due dates now, so that you can finish them up whenever and you'll get your results straight away. The course finishes basically on the 29th of October, and you'll probably have about 2 weeks after that to wrap up the last bits and pieces, but if you need to, please get onto that quickly, work on your quizzes, ask questions, get help if you need. I'll be around, and I'm very happy to answer questions and so on. Okay, I will dive into it. So this is just the worksheet for problem sheet 4.3 for quantum. So let's see, the energy in a photon of light with that wavelength. So we've got E equals question mark. We want to know what the energy is. Lambda equals 723 nanometers, but we'll write it in the correct SI unit, 7.23 by 10 to the minus 7 meters. And that's really all we have, the wavelength. But it is a photon of light, so its velocity is the velocity of light. So V equals C equals 3 by 10 to the 8th. So its velocity is just, sorry, that should be an equal sign. And so now we've got a velocity and a wavelength. So we've got the expression that says E equals HF. E equals Planck's constant times the frequency, but we're not given the frequency. But we do also have another equation that says C equals F lambda, or V equals F lambda for any wave, but for an electromagnetic wave, so light, radio, gamma rays, X-rays, all of the other things that are in the electromagnetic spectrum, the velocity is always C, so we just get that. So, sorry, that looks like an equal sign and it shouldn't. That's just an underline. I might even delete it just to make it clear for anyone who sees it later. So we want to know the frequency though, so we'll rearrange that to make F the subject. F equals C over lambda. So that means we can change this to HC over lambda. So give myself a little bit more room. Equals H. We've got the value of H up the top. It's 6.6 something, but I can never remember. 6.63 by 10 to the minus 34. Now this is one photon of light, so you'd imagine that the number we get is going to be fairly small. The actual energy of a single photon is not going to be huge. Times C, the velocity, which is just the speed of light, by 3 by 10 to the 8, divided by lambda, which is the wavelength, which is 7.23 by 10 to the minus 7. Now, dividing by 10 to the minus 7 is like multiplying by 10 to the 7, and then multiplying by 10 to the 8. So practically we're multiplying by 10 to the 15 or 16, times 10 to the minus 34, so we should end up with about 10 to the minus 18, somewhere in that vicinity as the answer. Let's run it through the calculator and see. That's my estimation. So that's maybe a slightly more sophisticated estimation than the usual ones we do. Minus 34 times 3 10 to the 8 divided by 7.23 3 by 10 to the minus 7. 2.75 by 10 to the minus 19. So I think I said 10 to the minus 18. I was in the ballpark. 2.75 by 10 to the minus 19 joule. This is an energy, so it's measured in joule. Okay, so that's that first one. The energy in a single photon is on that order. So 10 to the minus 19 joule. Quite small, but if you get a bunch of photons together, you can run the country on solar power. Obviously, there are vast numbers of photons coming from the sun to us every day. In terms of the strength and range of the strong nuclear force and the electromagnetic force, explain why nuclear fusion requires extremely high temperatures and therefore extremely high particle energies. So for nuclear fusion, we have... You could notionally do it with hydrogen, so a proton and another proton, but we typically don't. We typically do it with deuterium or tritium, which are isotopes of hydrogen, or with various heliums. So deuterium is basically, we sometimes call it heavy hydrogen, 1 proton and 1 neutron, and tritium is 1 proton and 2 neutrons. Those circles should all be roughly the same size because protons and neutrons are roughly the same size. So these are both hydrogens, but they are different isotopes of hydrogen. They would have electrons, but we're not going to worry about the electrons. We want to get those two to crash together because we want to get them to fuse, and they will fuse to form a helium. In this case, it would be 1H2, and we get into radioactive next week, and nuclear and so on. So if this is a little bit ahead of where we've got up to so far, don't worry too much about it because we do that next week. So that's a deuterium. It's a hydrogen with 2 nucleons in it. This is a tritium, a hydrogen with 3 nucleons in the nucleon number, and that's going to give us a helium, He, and that's going to be 2 and 5. In other words, the product is going to have 2 protons, and 3 neutrons, so for a total of 5 nucleons. Unless a neutron flies off, which it sometimes does, but in that case, a helium-5 is quite a sensible sort of isotope, plus a bunch of energy. We sometimes talk about it as gamma, or there's a number of symbols we use for it, but it's energy being radiated from this. So this is a fusion reaction. Now, what holds this new nucleus together is the strong nuclear force. So once you've got them really, really, really close, it's a short range but very powerful force, then they will merge and fuse, and the strong nuclear force will hold the new nucleus together. But to get them there, you've actually got here a positive thing and here a positive thing, which are going to repel each other using the electrostatic force. So the electrostatic force is the repulsion between these two positively charged things. And what we actually have to do is drive them together hard enough that it overcomes that repulsive force. So if you're holding 2 magnets, if you're holding one magnet, a bar magnet, on a bench, this is your north end of your bar magnet, and this is your north end of another bar magnet. If you push this one towards it slowly, probably that one's going to slide and move away, and they're never going to run into each other. But if you push this one towards it fast, you can kind of use momentum and speed and overcome basically you're using the momentum of this, the inertia of this one not moving, and you can get them to clack together. So if this is effectively what we're doing. We're taking 2 things that repel each other, slamming them together at very high velocity, and that allows us to get them close enough that the short range but more powerful strong nuclear force takes over. So we could imagine this another way. We could imagine it as a potential energy diagram. So if this is distance and this is energy for one of the particles, there's kind of a well. There's a potential energy drop where the strong nuclear force takes over, but before that there is an energy hill of the electrostatic repulsion force. So it takes work, it takes doing energy to get up and over that hill. So again, if you are on your bicycle and you get a good run up, if you don't get a good enough run up at the hill, and then you'll get part way up and roll back down again. If you get a good enough run up and have enough momentum, you'll get up and over and down into the gap. And the analogy breaks down because you can't actually jump over like you might on your bicycle. So the analogy is not perfect, but the notion that you have to have enough speed coming in, and remember that speed corresponds to the temperature of things that are moving around in a gas, which these are. So basically, the hotter the temperature, the faster the velocity of the individual particles. So you need extremely high temperatures. You need on the order of the heart of the sun type temperatures, tens of millions of degrees, to get these hydrogen atoms, hydrogen isotopes, close enough to allow fusion to occur. And in fact, I mentioned that there would be electrons orbiting, but in fact there wouldn't, because at those temperatures you've got plasma. So the sun is made up of plasma where the electrons are separated from their nuclei. There's enough energy that the electrons are all the way out of their orbitals and floating around, which is the state that plasma is. So in fact you would just have the nuclei floating around in the plasma. Well, not floating around, whizzing around, because they're at extremely high temperatures. So they're zapping around at extreme speed. And every now and then they'll collide at the right energy and the right orientation to actually fuse and release more energy and make things even hotter, which is how you get a chain reaction. So I've kind of talked through it. I won't write a blurb. It's kind of a qualitative question, but I've drawn some pictures, talked about some analogies and talked through it. So hopefully that means that you've got some sense of why those temperatures are required to allow fusion to occur in the face of the electrostatic force and its strength. The electrostatic force, weaker but longer range. Gravitational force, weaker again but even longer range than electrostatic. Briefly explain the features of the photoelectric effect and explain why it is considered to be evidence for light having a particle nature. Okay, so if we do a diagram, here's our sample of metal. I guess it doesn't actually have to have a dimension, but it's just a piece of metal, and we're shining light on it. If we shine this long wavelength light on it, it'll reflect, but all we'll get is light reflected back. So we'll get photons going in, photons coming out, nothing else happening of a particular metal. If we shine a short wavelength, high energy light at it, then what we'll actually see is electrons coming out, so flying out. Those are speed lines, in case it's not clear. So if we put in photons of the right energy, we will get electrons being ejected from certain metals, photoelectric metals, and if it's the wrong energy, we won't. Now I'm actually going to redraw those because I'm going to draw them as photons. So a photon really is a little packet of waves, but the little packet of waves still, let's draw that better, still has long wavelength and short wavelength, still has a frequency, still has a period, etc. So if we send a packet of longish waves in, we get nothing out. If we send a packet of shortish waves in, we get photoelectrons out. If we send even shorter waves in, we get actually let me even draw that even more better. So I'm kind of doing a continuous improvement process, we get photoelectrons coming out. So we might just give him one speed line this time. And if we send in even shorter wave, so even higher energy photons, right? We've got that E equals HF, higher frequency, higher energy. Then we get photoelectrons coming out with more velocity, traveling faster. So the energy of the photons coming in leads directly to the amount of energy of the electrons coming out, if any electrons come out at all. So basically the key is that if light behaved purely as a wave, then it could keep on waving and waving, keep on bringing more energy in until it had enough energy to eject a photoelectron. But in fact it doesn't. That's not what we observe. In the photoelectric effect, you can shine an extremely bright light of too longer wavelength, too low in energy on it forever, and you won't get any photoelectrons. But as soon as you shine even a dim light of a short wavelength on it, you will actually start to get photoelectrons ejected. So it's about the packets of energy and the amount of energy that comes in with each packet, and whether that's sufficient to give the electron the energy it needs to escape from the surface or not. So again, I could write a blurb here, but I won't bother. I think the video and the verbal discussion is probably more informative. But there are also some really good simulations and visualizations on the web of this and of how we tell how fast the electrons are going and a whole variety of other things around that. So hopefully a helpful thing. Okay, we'll keep going. So to illustrate the concept of the de Broglie wavelength, I tend to tell students even an elephant has a de Broglie wavelength. So let's calculate the de Broglie wavelength of an elephant. An African elephant can have a mass up to 6,000 kilograms. Actually, you might remember from last week's recording, if you watched it, or if you were live in the Collaborate session, that I also often tell students that riding fast on my motorbike leads to me living longer relative to everybody else, or being younger relative to everybody else because of relativity. But what I then illustrated was that, in fact, that effect is real, but it's so negligibly small that it doesn't mean anything. And to some extent, I think we're going to discover the same thing for elephants, because I don't think, if you've seen video of elephants running fast, I don't think you saw them moving in a wave nature structure. So let's actually have a look and do the maths on it. So African elephant can have a mass of up to 6,000 kilograms and move it up to 40 kilometers per hour or 11 meters per second. Calculate the wavelength of a large elephant running fast, and comment on why we don't observe the wave nature of elephants. All right, let's go up and find our equation for Count Louis de Broglie. Lambda equals h over p, and p is just the momentum, mass times velocity. So lambda equals h over mv. All right, we can do that and remind ourselves of h, 6.63 by 10 to the minus 34. So lambda, the wavelength, equals h over mv. Let's put in our data again. Lambda is question mark. We don't know what it is. It's going to be in meters. It's a wavelength. H is just h. It's a constant, so we won't bother writing it out here. The mass is 6,000 kilogram. That's already in SI units, so I didn't say 6 ton. And velocity is 11 meters per second. So again, it's going to be small, isn't it? So we've got 6.63 by 10 to the minus 34. Yep. Over 6,000 times 11. If I run that through the handy dandy calculator, I get, because this number is larger than 1, so it's going to make our number even smaller than 10 to the minus 34, which is already pretty dang small. So in fact, we get 1.00, which is neat, by 10 to the minus 38 meters. So 10 to the minus 38 meters is extremely tiny. It's on the order of Planck space, Planck wavelength, which is the kind of size of the singularity from which the Big Bang occurred. It's an extremely, extremely tiny number. And certainly if an elephant moved by that much, we wouldn't notice it. It's completely negligible, so we can't observe it for that reason. It's just too small to be able to measure. It's things down at the atomic scale, at the scale of photons and electrons, where we actually measure measurable wavelengths. So let's have a quick look at the next question, because I seem to recall we might be doing just that. No, maybe not. All right, let's just go. Okay. Nice. Okay. Let's do one, because I think it probably makes sense to do an example of this. So let's find the de Broglie wavelength of an electron. So we still want to know that. Mass of an electron is 9.1 by 10 to the minus 31 kilogram. It's just one of those things I never memorized, but I did enough problems with it in there that I remembered. And let's say we do it at a velocity of, let's do 10 to the 6 meters per second. That's 10%, 3% of the speed of light, roughly. So 10 to the 6 meters per second. That's quite a manageable sort of velocity for an electron to travel at. Is 10 to the 6 meters per second. In fact, electrons travel at significant proportions, 0.9, 0.95 of the speed of light under various conditions. So lambda equals h over mv again, equals 6.63 by 10 to the minus 34 over 9.1 by 10 to the minus 31 times 10 to the 6. 10 to the 6 is about, so we can see that that's actually going to be about 10 to the minus 34 divided by 10 to the minus 25. So it's going to be 10 to the minus 9, something like that, roughly, very roughly, because one's okay, 7.3 by 10 to the minus 10. Now remember that this is an electron, it's not a photon, it's not a light particle, it's an electron, but that wavelength is 0.75 of 1 nanometer. Right, a nanometer is 10 to the minus 9, this is 7.3 by 10 to the minus 10, or 0.73 by 10 to the minus 9. So it's 73% of the size of 1 nanometer. Light has a wavelength on the order of 400 to 800 nanometers. So this is about 100th or about 1,000th the wavelength of a photon. So the wavelength of an electron is much smaller again, because the thing is much bigger than a photon, has much more energy at rest. So, but it's nonetheless, it's relevant. You know, at the size of an electron, at the theoretical width of an electron, which isn't even really a thing because they behave more like mathematical points, but this kind of wave nature is relevant for an electron, where it's not relevant for an elephant. Okay. I should just note that this is an electron in case anyone tries to read it without listening to the video and is mystified. You know, those people who don't have the massive electrons memorized so that it's immediately obvious that it's an electron. I'm joking. Briefly explain why the existence of the emission spectra of atoms of particular elements is evidence that energy is quantized. So hydrogen is the simplest one, so let's use it. So it has 1 proton, 1 electron. That 1 electron can be in the s orbital, or it can be, now this is tricky, the p orbital is actually not spherically shaped like this. Oops, that's horribly not spherically shaped. I'll try. I think I may have mentioned before that allegedly psychopaths can draw perfect circles by freehand. On this test, I'm safe from being a psychopath. So we could imagine that as being the S and that as being the P, but in fact the P orbital is made up of 3 dumbbell shapes, one in the y-axis, there, like almost teardrop shaped, one in the x-axis, and one in the z-axis, so coming out of the board and going into the board or the paper. So that's what the p orbital actually looks like in terms of the shapes of where the electrons are. But in terms of energy and distance from the nucleus, we can kind of imagine it as that. So the electron mostly hangs out in here because that's the lowest energy state. If a photon comes in, it can boost it from there to there. So the electron now has more energy, and then the electron can drop back to that lower energy state and release a photon. Now, the photons that come out are the ones we're interested in because they will always have the same wavelength. The ones coming in can be anything. It can be white light. If it doesn't have enough energy, it won't boost it. If it has just enough energy, it will boost it. If it has too much energy, it will boost it and release a smaller photon. So the excess energy will be released. It will absorb what it needs in order to rise, but the excess energy will just be released. So the photons being released correspond to the differences between these energy levels, and there are a number of these energy levels. So in fact the various bits of the p are at the same energy levels, but then you'd have the d orbitals. The d orbitals are, so the s orbitals are actually spherical. The p orbitals are these shapes. The d orbitals, there are 5 of them, and some of them are shaped like this, like flower petals, and some of them are shaped like this, like a teardrop that way, a donut around the middle, and a teardrop that way. And so on. So they get more complicated as we go. There are the f orbitals as well, which I'm not going to attempt to try and draw. But basically, the energy is quantized because if these photons instead, the ones coming out, were just white light, just a complete continuum, just a full, not a detailed spectrum of a line here, line here, line here, line here, but just a broad spectrum, that would mean that these energy levels could be arbitrarily far apart. You could have an electron orbiting at any distance, to use the planetary analogy. But that's actually not what we observe. The energy is quantized. The energy levels are set by particular quanta of energy, and the electron can only occupy these quantum positions. And notionally, that means it doesn't even travel between them. It kind of blips from one to the other without covering the intervening space, if you want to think about it that way. Similarly for these, if you think about it, in this d orbital, the electron has a probability of being here, probability of being here, probability of being here, probability of being here, 0 probability of being here, but yet it's found sometimes here and sometimes here. So it goes from this side to this side without crossing the intervening space, which is pretty freaky. That's one way of looking at it. The other way of looking at it is that these aren't actually places, they are clouds of the probability of finding the electron. The electron's actually smeared out across this area until we observe it and force it to be in a particular place. But that's a little bit more challenging. Now I'm going to have to take that phone call, so I will be back in a moment. Okay, going again. I think we're just about done. The machine tells me that that's been about half an hour. And maybe I was starting to digress anyway, but the fact that there are these finite, very specific levels at which the orbits can actually occur is evidence for the notion that energy is a quantum phenomenon rather than a continuous phenomenon, whereas a classical phenomenon, so in our solar system we have planets at a number of different distances, we have the asteroids at a number of other different distances, we have comets and meteors, whole variety of things that orbit the sun at any arbitrary distance that they want to. So that's a classical level system. At a quantum level system, you don't have that. You can't have an arbitrary orbit. You have to have these specific quantized orbits, and the emission spectra are evidence for that particular phenomenon. Okay, I hope that's relatively clear. It is obviously a very, very quick précis and run through of quantum theory. It is a large and complex topic. Really, quantum theory is the theory that explains what's going on, and quantum mechanics is the maths we do to help us actually solve it. So there's a whole variety of maths. Most of it involves I, the square root of -1. It turns out that you need those imaginary numbers, as they call them, the square root of -1, to do quantum mechanics properly. There's nothing else that will actually work and give you the right answers. So quantum mechanics does a lot of that. It does some matrix algebra and a whole variety of other things that allows us to calculate the probabilities of finding electrons in particular places or other quantum phenomena. And that kind of underlies electronics and a whole variety of other things that we use in our everyday lives. Semiconductors wouldn't work without our understanding of quantum. Okay, thanks very much, and we'll see you next week for radioactivity, radiation, nuclear stuff. Have a good one. See ya.